Hi, everybody. This is your third video in section 1 of Unit 5. So this video is on conditional probability and independence. So let's just go ahead and jump into it. So in the previous video, we talked about some very basic probability rules, like the addition rule, the complement rule, things like that, right? Conditional probability is a little bit different, but it's exactly what it sounds like. You calculate probabilities based on a condition that is given to you, right? So rather than looking at, say, a whole two-way table, you would only look at one part or one section, right? So the definition of conditional probability, okay, is it's the probability that one event happens given that another event has already happened. Okay, and the key word here is this word given. Okay, whenever you see the word given, that usually means that you're dealing with a conditional probability. Okay, so given, that's your key word right there. Okay, the notation for conditional probability is this vertical line. Okay, so your notation here is probability of A, and then you have this vertical line, and then B. So what that literally translates to is the probability of A given B. Okay, meaning we're trying to calculate the probability of this event A given that we already know that event B has occurred. Okay, so this vertical line literally translates to the word given. Just like when we talked about this upside down U literally means the word and this regular looking U literally translates to the word or. Okay, so there is a formula that we use. Oops, sorry. Okay, there is a formula that we use to calculate conditional probability. Okay, and this is what it is. So the probability of A given B is equal to the probability of A and B, so meaning the probability that they happen together, divided by the probability of B. Okay, whatever comes second, whatever event listed second is the restricting event. Okay, so rather than dividing, say in a two-way table, rather than dividing your cell by the total in the table, you're going to divide it by the total in this category, right? Because if this condition is already given, then that means I only care about the people or the cells in that particular category. Right? I already know that it's true. So like that second event is true. So I can ignore everything else and just focus in on that category. Okay. So there is an example in your notes that you can look at where it kind of shows you how they isolate individual rows or columns and how the denominator will change depending on which variable is listed second. Because that second variable is always the restricting event. Okay, but I think it's easier to see what happens when you can actually see it like in action. Okay, so this question here is asking what's the probability that a randomly selected student voted red given that they are a sophomore. Okay, so the condition or the thing that we already know is true is this. We know that they're a sophomore. So what that means is I don't care about the freshmen, I don't care about the juniors, I don't care about the seniors. I only care, and I'm going to focus in on the sophomores, right? So it's almost like you can draw like a bag around it or like a bag of marbles, circle it, right? That's the category that you're focusing in on and the category that you care about, okay? So rather than dividing this fraction by the total in the table, which is 2,500, we're going to divide it by the total in my restrictor category, which is 625. Okay, and then I'm trying to find the probability that a student voted red given that they're a sophomore. So I'm in my sophomore circle, right? And then I'm looking for the red, those who chose red within that category. Okay, so the way that this is written, okay, the way that you write this is it's the probability of red given that we already knew that that person was a sophomore. Okay, so that equals the number or the probability of both of those together, which is the intersection of the two categories, right? So we have sophomore here and red here. So the intersection of those, that's your and probability, is the intersection of those two, divided by the total in the restrictor category, which is 625 in this case. So 167 divided by 625, okay? And that actual decimal is 0.2672, okay? All right. So what I want you guys to do now that you've kind of seen an example here, is I want you to try on your notes page a couple of these questions. So I want you to try 11, 12, 13, 14, and 15. Okay. So I want you to try these 5 right here. So again, you're calculating some given probabilities, and some others you're doing some multiplication. And what you're going to find is some of these values will be equal to each other. And others won't, uh, depending on the relationship between the variables, which I'll get into a little bit later in this video. Okay, so pause the video here, try questions 11 through 15 in your notes, and then check back with me in a minute to see if your answers are correct. All right, folks, so let's check your answers here. So for number 11, this is asking for probability that the student is a senior given that they voted blue. Okay, so blue is my restrictor category. So I'm only going to look at that column and ignore everything else. So the probability of both senior and blue is 288, or the number is 288 divided by the total in the restrictor category, which is 1200. Okay, so the way that this should be written is senior given blue, right, and you get 0.24. Okay, for 12, this is asking what's the probability that a student voted blue and is a junior. So there's no condition here, right? We're not saying we know they voted blue or we know they voted that they were a junior. We just want to find the the intersection probability, the and probability. So if you're finding an and probability, you don't restrict anything. So you're going to divide by the total in the table rather than the total in like a restricted category. Okay, so there's 276 people that voted both blue and were juniors. And then because it's not a conditional probability, I'm dividing by the total in the table, which is 2,500. Okay, so I got 0.1104 when I did that. Okay, 13 asked you to multiply probability of blue and probability of junior. Okay, so probability of blue is the total in that category, 1,200, divided by the total in the table, 2,500. Do the same thing for the juniors, and when you multiply them together, notice that you get the same number. Okay, you get the same number that you got in the previous question. Okay, so there's a reason for that, and I'm going to talk about what that reason is in a little bit here. Okay, 14 had you do a similar thing, so they wanted you to find the probability of red and freshman. So there's 364 people who voted red that were also freshmen, divided by the total in the table, because there's no condition here, is 20 of 2,500, so you get 0.1456 when you do that. Okay, for 15, this time when you multiply their probabilities, you get a different answer. Okay, so 16 on this, on your notes, ask what's happening with 14 and 15? Like, why weren't those answers the same? Like 12 and 13 were. Okay, so the reason that they're not the same is because we have rules for something called independence. Okay, so the events, that should say blue and junior. Blue and junior are independent. okay? And the events, oh, right? And the reason we know they're independent is because you got an equal probability. Uh, for the and probability and the multiplied probabilities. Okay, the events red and freshman are not independent because you get not equal probabilities. Okay, so this goes into, okay, well, what is independence? Like, what is that? What do you mean by that? And why are we doing all this multiplication? Okay, so the last little part of this video is I'm going to talk to you about this thing called the multiplication rule and this idea of independence. Okay, so independence in statistics, the definition of that is that the occurrence of one event or adding a condition, okay, does not change the probability that another event will occur. Okay, so the definition is the occurrence of one event doesn't change the probability that another event will occur. Okay, the classic example that I give people is thinking about a deck of cards, right? So let's pretend that we have a deck of cards, right? And I pull a card at random, okay? And I show it to you, right? I pull a random card and say my random card was the two of hearts, okay? And I ask you, what's the probability that out of my 52 cards that I randomly pull the two of hearts? Well, that's 1 out of 52, okay? Right? So if I gave you more information at the start, if I told you that the card was a heart, right? If I give you a condition, okay, I tell you before I show you the card, right? I tell you that the condition is I'll tell you that the card is a heart. I'm not going to show it to you, but I'll tell you the card is a heart. And then I ask you, what's the probability that that card is a two of hearts, right? Well, if I already know that the card is a heart, rather than dividing by 52 here, I'm going to divide by 13 because there's only 13 hearts. So me adding this extra condition changed the probability. So these two events are not independent. Okay? Now, instead, right, and I'm going to write at the bottom of the screen now. Instead, let's say I I told you that or rather I pulled a card, right, at random, and I said, I want to know what's the probability that this card is a diamond, right? Well, there's 13 diamonds in the deck, and then divided by the total number of cards, which is 52, and that reduces to 1/4, okay? Okay, so again, I'm going to pull a card, and I'm going to say, I'm going to give you a condition. Okay, the condition is that that card is a 7, right? And so now I'm asking you, okay, what's the probability now that I've pulled a diamond, given that I already know that the card is a 7? Well, there's only 4 sevens in the deck, right? The 7 of hearts, 7 of diamonds, 7 of spades, and 7 of clubs, okay? And there's only one of those, right? One of those 4 cards that is a diamond if I already knew it was a 7, right? So here I get these equal probabilities. So me adding the extra condition and telling you that the card was a 7 did not change the probability that that card was a diamond, right? That probability stayed exactly the same, which means those two events are independent of each other, okay? So the formula, right, the actual formula here is, oh, hold on. Okay, here we go. So the actual formula is the probability, what you're checking is, does the probability of A given B equal the probability of A? Okay, we're saying, does adding this extra condition, B, change the probability that A will occur, right? So what this means, just in layman's terms, is that adding the B restriction doesn't affect the probability that A will occur. Right? It doesn't actually affect the number, right? So that's literally what this formula means, okay? We can then take this and use it to build the general multiplication rule, okay? Which you see on the screen, on the left side of your screen here, okay? Because if you recall, the probability of A given B is the probability of A and B divided by the probability of B, right? So the multiplication rule is the probability of both events happening together, A and B, is equal to probability of A times probability of B given A. Okay, right? Essentially what I did here is took this probability of A, which is like the denominator of this fraction here, except I switched it, right? Because this is A given B and this is B given A, but it's the same idea. Actually, hold on. I really should have thought this through a little bit before I did this. 1 second. Oh dear. I'm over here erasing things. Here we go. Okay. I'm going to write this slightly differently than the way you see it on the slide. Okay. So probability of the general multiplication rule is, if you want to find the and probability, right? That would be the probability of B times the probability of A given B. Okay? This essentially is a multiplied out version of this general conditional probability formula. Okay? Basically, what I did here is we said this is probability of A given B equals probability of A and B divided by the probability of B. Okay, what I did is multiplied both sides by probability of B. And I probably should say, you don't have to write all of this out, like this explanation that I'm writing out for you here. I'm just trying to show you where this rule comes from, right? And how it's all based on this like fundamental conditional formula, right? So when you kind of resolve this equation to get probability of A and B by itself, these cancel out. So what you end up with is this probability of A and B equals probability of B times probability of A given B. Okay, so that's your general multiplication rule. Okay, What you saw in the previous problems up here, when you had these equal probabilities, okay, is our multiplication rule that's specifically for independent events. Okay, so for independent events, this value, probability of A given B, is just replaced by the probability of A. Okay, so rather than writing A given B, you can just write probability of A, because remember, for independent events, A given B and A are equal. So you can substitute them out, like for one another, okay? So my general formula then for, hold on. My general formula then for independent events is that let's change that color, because that green is really hard to see. Okay, so for independent events, the rule is probability of A and B is the product of the individual probabilities. Probability of A times probability of B. Okay, but this only works when the events are independent, right? So in the previous examples that we did, the events blue and junior were independent. So the and probability was equal to the product of the individual probabilities. The events red and freshman were not independent. So the and probability was not equal to the product of the two individual probabilities, okay? So if you are asked to determine if two events are independent, there's two ways that you can do that. You can either calculate the conditional probability and see if it's equal to the non-conditional probability. So that's like the definition method, where you can use the definition, or you can use the multiplication rule and see, does the and probability equal the product of the individual probabilities? If it does, then the events are independent. If it does not, then the events are not independent. Okay? All right, so give me just a second, you all, to clear some things off my screen, and then I'm gonna help you fill in this two-way table with this word problem with some information here, and then there's a couple of questions for you to try out. So give me just a sec to clear some things off on my screen, and I'll see you back here in just a second. Okay, so really quickly before we try this one last example problem, I wanted to show you these are your two methods that you can use to check for independence, okay? So the one you see on the left side of your screen is what I called the definition method. So we're checking to see, does the probability of blue change when you add the extra condition of junior, right? So we're seeing, does probability of blue equal the probability of blue given junior? So you have those two probabilities, and if you actually figure out what those are, you get the same value for both, meaning that those events are independent, right? For the red and freshman events, we were checking to see, okay, does the probability that the person chose red, does that change if we add on the extra condition of that person has to be a freshman? So when you calculate those two probabilities, you get two very different numbers, meaning that adding the extra condition of freshman changed the outcome and changed the probability of randomly selecting a person from that group that chose red as their favorite color, right? So what you see on the left side of the screen is your definition method. What we did in questions 12 and 13 and 14 and 15 is the multiplication method, where you check the and probability and then the multiplied the product of the two individual probabilities and see if they are equal, right? For blue and junior, you ended up with equal probabilities. For red and freshman, we ended up with probabilities that were not equal, right? Okay, so last bit here, we have this sample problem where they just gave us a little bit of information and told us that there was 1,000 students, and we have to now figure out, just based on the information they gave us, how many people fit in each of these categories. Okay, so we have female students and male students. So those are one of my my margin categories, right? So female students and male students. Okay, and then they were asked to choose the school mascot, right? And the three options were Wolverine, mouse, and dragon. Okay, we were told of those voting, 54% were female. Okay, meaning that this total has to be a total number of females has to be 54% of the total number of people, right? So that would be 1,000 times 0.54, which is 540, right? So this number is 540, okay, which means that the total number of men is 460, so that the total number of people would be 1,000, okay? The next sentence says an overwhelming 60% chose the Wolverine, okay, meaning 60% of the whole population chose Wolverine. So 1,000 times 0.6, which is 600, okay? And then it said with 55% of them being male, okay? Meaning that I have a condition that I've met. The Wolverine is my condition, right? And 55% of those who voted for the Wolverine were male, right? So to get this number, right, I would have to do not 1,000 times 55%, but 600 times 55%, right? So when you do that, you get 330. Okay. All right. Next, this says 20% of the girls thought it would be great to have a mouse as the mascot. Okay. So female is my restriction, right? And then mouse is my other event, right? So to get this cell, right, I would have to do not the total times 20%, but the total number of females times 20%. So 540 times 0.2, which is 108. Okay. And then the last sentence here says only 5% of the males agreed, right? So again, that means not 5% of the total, but 5% of the males. So 460 times 0.05, which is 23. Okay, and now I have enough information to fill in the rest of the table. So I know the total for mice is 131 by adding these two values. Okay, I know that down here, the total for dragon then has to be 1,000 minus 731, which is 269. Okay, I know that the total number of males who voted for dragon would have to be 353 subtracted from 460, which is 107. Okay, I know that the total number of females who voted for Wolverine would be 600 minus 330, which is 270. Okay, and then I know that my total number of females who voted for dragon would be, there's a couple ways you can calculate this, but the easiest is to do 269 minus 107, and you get 162. Okay, so now that you have this two-way table filled in, you have all the knowledge to attempt these 5 problems here, okay? So that's what I would like you to do. Pause the video, use this two-way table to calculate these 5 probabilities, right? So pause the video, and I'll see you back here in a second to check your answers. All right, folks, so here are the final answers. So check your answers against mine. So first question asked to find the probability of a dragon mascot. So there were 269 that voted for dragon, divided by 1,000, so 0.269. Okay, the second question asked for probability of choosing a mouse or female. So remember, when you're calculating an or probability, that is the addition rule. Okay, so add the sum of the 2 categories that you're looking at. So there's 131 in the mouse category and 540 in the female category, and then subtract out what they have in common, right? Because these 108 people are counted twice. So that's exactly what I did on this side. I ended up with 563 over 1,000, which equals 0.563. Okay. If you have divided any of these up to this point by a number that was not 1,000, you did these incorrectly, right? The only time you're going to change the denominator of your fraction in a two-way table is if you are looking at a conditional probability. So you want to look for words like of or given, right? That will tell you that you're looking at a conditional probability. Okay. For number 3, it says, what's the probability of selecting male and dragon? So remember, you're just looking for the intersection of those 2 categories, right? 107 divided by the total in the table, which is 1,000. Okay. Question 4 said, given that the student is female, what's the probability that she voted for the dragon? Okay. So female is my restriction category. So I'm only going to focus on those in that category. I don't care about anyone else in the table, right? And then I want the dragon within that, which is here. So 162 divided by 540 would be the answer there, and I got 0.3 when I did that. Okay. Then the last question here is show that these 2 events are not independent. So I used the definition method here. And the reason I did that is because I already had most of the probabilities I needed. In number 4, I calculated the dragon given female probability. And in number 1, I calculated the dragon probability, right? So in looking at my general definition or my general formula, I have A given B, dragon given female, and A, dragon, right? So I can just compare those 2 and I end up with, no, they're not independent because you get 2 different numbers, okay? You could use the multiplication method here by figuring out what the and probability is for dragon and female, and then figuring out what the female probability is, and multiplying the dragon probability with the female probability and see if it equals the intersection, the and probability, right? But like I said, because you already calculated a lot of these for the conditional and the definition method, it's a little easier, okay? So what we see is that the addition of the female restriction changed the probability of randomly selecting a person who voted for dragon as the school mascot. All right, you also, that is the end of this video. In the next video, which is the last one in this section, we're going to talk about and kind of bring all of these ideas together in visual formats. We're going to talk about Venn diagrams and we're going to talk about tree diagrams. So I will see you in the next one. Bye, everybody.